On to another AIME problem, the 2016 AIME 2, question 7. Squares ABCD and EFGH have a common center, AB parallel to EF. The area of ABCD is 2016, and the area of EFGH is a smaller positive integer. Since IJKL is constructed so that each of its vertices lie on ABCD and each vertex of EFGH lies on a side of IJKL, find the difference between the largest and smallest positive integer values for the area of IJKL. And so we have three squares, not really inscribed, but so that the vertices are on the edges of the larger square. So let me draw some of this. ABCD is the largest, so I'll draw that first. ABCD. And I'll make sure not to draw the any of the special cases here, any of the largest or smallest just yet. So inside ABCD, we have a square where each of the edges, or each of the vertices are on the edges of ABCD, and that is the square IJKL. They don't specify which vertex is on which side. And then inside that, I have yet another square that has the same area, sorry, not the same area, the same center as the ABCD. So that's E, that's not an E, E, F, G, H. And these are parallel. Now, what happens is this. So there's a lot of similar triangles in here. So this triangle here is similar to this smaller triangle here. And we have the similarity ratio going on, which tells us that the area of the first triangle, the area of the second triangle, and the area of the third triangle must form a geometric sequence. And I'm going to consider the smallest triangle, IJKL, the smallest possible triangle first. So in here, this is the way to get the smallest. If I take my outer triangle and connect up the midpoints, and then connect up these midpoints, this is as small as it gets. If you sort of turn this square, I said triangle, turn the square further, you get larger squares again. So in here, the largest square, head area 2016. Because we're really sort of taking 1/2 of each of these four quadrants, we're really just dividing 2016 by 2 and getting 1008. And it happens the same way again, where I'm dividing each of the quadrants of the middle square by 2. I get 504. And you can see, of course, all right, yeah, they all have integer areas, and this will be the smallest. I cannot get any smaller than this because and you can see in here, if I'm not at the midpoint, the squares are larger. So this right here is the smallest possible. So the question comes in, what is the largest possible? And the answer comes about because I need to have a geometric sequence with integer values A1, A2, A3. We know that A1 is 2016, which has a prime factorization. Let me double check my work. I did it already. And it's worth doing the prime factorization of each of the years because it shows up a lot in all these competitions. of 2 to the 5th times 3 squared times 7, which means that if I want to take 2 steps in here, and I cannot divide by more than a half, okay? There's no possible way, because then the sides would not fit on the squares anymore. But I will be able to do this. I can take out 2 squared times 3 2 times and not run out of 2's and 3's when I divide it out twice. But I want to have the largest one possible, so 2 squared times 3 is 12. And the largest integer I can bring in there is 11. That's the next largest integer less than 12. So I can do 2016 times 11 over 12, and that's going to give me my middle, IJKL, value. So let's see, 2016 divided by 12, well, 2016 divided by 4 gives me 504. 504 divided by 3, let me make sure I just do it correctly. So I get 120, 6, 24, 168. Okay, so 168 times the 11. So I have 168 plus 1,680. 8, 4, carry the 1, 8, 1. So the largest middle square I can get is 1,840. The smallest one is 1,848. The smallest is 1,008. So to get the difference between the largest and the smallest, just subtract 1,848 minus 1,008, and that gives me 840. If you have any questions, post them in the comments below, and I think I'll get through one more problem before I call it for the night.